determine the Hamiltonian would depend only on the weight of that and not on the total number of qubits. Take a computer which has 100 qubits versus 1,000 qubits. The assumption is we pay the same price for a 10-qubit operator in either case. That's different than Nielsen's definition.
So,
but still, we still require the largest value of I to be 4 to the n in order that the maximally complex states have complexity of order 4 to the n. There's only one way to do that, and that's to take the coefficients of the I here, of I. I'm assuming it's now diagonal. To be of order
一丁だよね。ついた。ああ、一丁だよ、つきました。
To this lecture in the around the country, from around the state, to talk to you about new developments in astronomy. This outreach series is co-sponsored by 4 important organizations: NASA's Ames Research Center, one of the premier NASA centers in the country; the Foothill College Astronomy Program, offering both day and evening classes in astronomy; the Astronomical Society of the Pacific, which since 1889 has been presenting materials and information about astronomy to educators and the public; and the SETI, or the Search for Extraterrestrial Intelligence Institute, which has an ongoing program looking for life in all forms in the universe. Tonight's speaker is Dr. Michael Bush, who works at the SETI Institute. Dr. Bush is a planetary astronomer based at the SETI Institute, as I said. His research focuses on characterizing near-Earth asteroids. Fellow at the University of California in Los Angeles, and at Radio Astronomy Observatory before starting as a research scientist at the SETI Institute in 2013. Asteroids are his specialty, and we wanted to tell you all about the science, the exploration, and the danger that asteroids represent. He calls his talk Rubble Piles in the Sky. Ladies and gentlemen, please welcome Dr. Michael Bush.
All right. Thank you, everyone, for coming out tonight, and thank you to everybody who's watching this on YouTube several months from now. So, again, I'll be talking about near-Earth objects, and specifically near-Earth asteroids. But I want to give a bit of context, what they are, where they are in the solar system. So we're going to start on a somewhat larger scale. This is a plot of the solar system out to the orbit of Jupiter, as of last week when I put these slides together. You can get the most current version of this from the International Astronomical Union's Minor Planet Center. They make a new version every day. So we are here on Earth, which is just off to the left of the Sun. I realize people watching this online will not see the laser pointer, so I'm going to try to describe what I'm pointing at. We have the orbits of Mercury, Venus, Earth, Mars. We go out. Out here is Jupiter. Jupiter itself is down in the lower left right now. And then everything else is a different small body orbiting the Sun. There's a lot of stuff out there. We have the main asteroid belt between the orbits of Mars and Jupiter, which is the green dots. We have the Trojan asteroids that share Jupiter's orbit 60 degrees in front of the planet and 60 degrees behind. And then we've got comets passing through. But what I'm talking about tonight are all the red dots in the figure. Those are the near-Earth asteroids. Now, near-Earth is only near on the scale of the solar system. When we say near-Earth, we're talking about objects that are orbits around the Sun that come within 50 million kilometers of the Earth's orbit, about 30 million miles, at some point in that orbit of theirs around the Sun. So that's a long distance by the standards of the size of the Earth. It's nearby on the scale of the solar system, where it's 150 million kilometers from the Earth to the Sun, 93 million miles, give or take, depending on the time of year. And Jupiter's orbit is about 1 billion miles from one side to the other side. So that's how much space we're dealing with here. There's 1 million asteroids roughly in this figure, many hundreds of thousands. There's even more empty space. They were playing the Star Wars music earlier, before the talk. This is not like Star Wars. The asteroids are not all piled on top of each other. You don't have to dodge your spacecraft around them. This makes sense intuitively. You go out at night, an area with a dark sky, you look up, you see stars. You don't see asteroids blocking your view every which way. The asteroids are as thinly spread as a grain of dust on one side of the room from a grain of dust on the other side of the room. That's how much empty space we're talking about here. Now, the near-Earth objects that we currently have that are able to pass near the Earth right now are not 4.5 billion years old on those orbits. Those orbits are not stable. Over millions of years, they can fly by the planets, they can fall into the Sun, which is kind of dramatic when it happens. They can get thrown out of the solar system completely. They can get broken apart by a couple of different ways. These asteroids have all only been on their current orbits for perhaps a few million years. They're constantly getting removed and replaced. The near-Earth population is coming from the main asteroid belt. Objects in the main asteroid belt get scattered inwards, typically by gravitational interactions with Jupiter, Mars, to some extent Saturn, and this constantly replaces near-Earth asteroids that are destroyed. So the near-Earth objects that we're seeing are remnants of escapees from the asteroid belt. The asteroid belt in turn represents remnants of planet formation. The reason there is no large planet between the orbits of Mars and Jupiter is that Jupiter happened first. And it became so massive so quickly that it started scattering the orbits of everything in the asteroid belt around. Collisions between the asteroids were very, very fast. They erode rather than accumulate into a single large object. So the largest few asteroids, Ceres, Vesta, others of that size, hundreds of kilometers wide, are 4.5 billion years old, the age of the solar system. Everything else is remnants of asteroid-asteroid collisions over the last 4 billion years. So almost a collisional cascade. So we're trying to understand, in some sense, the origin of the solar system. It's 4 billion years old, but we have to on a lot of the larger objects. So this is a collage of various asteroids that were visited by spacecraft. There's a bunch down here, but I don't have
なん
time
で
to
トレイルランニングができるの？
Emily Lakdawala at the Planetary Society put this collage together. She's written extensively on all the different planetary systems. So the asteroid Lutetia here, the single largest one on this picture, is 130
めっちゃ辛いわ。
kilometers, a bit over 80 miles wide. It's probably 1 million years old, but you can see it's lost large sections of its volume to collisions. Things just a little bit smaller than Lutetia got broken up completely. And all the
こんにちは。
other asteroids
Good
that
job.
we see over here are
Good job.
accumulated debris from previous asteroid-asteroid collisions. They're piles
こん
of
にちは。
hence rubble pile. Like the top. You'll also notice a wide range of colors here. There is in fact an asteroid over here on the right. It may seem almost invisible because it is incredibly dark colored. There's a large section of asteroids called C-class objects, carbonaceous objects, that are very rich in carbon compounds. Black, tarry gunk.
よくトレイルができる。
When the solar system formed, they never heated up very much. So they never lost these carbon compounds, which some larger objects did. When gravitational heating, as they accumulated radioactive isotopes, eating them up, they melted and boiled off the carbon compounds into the water. The C-class objects didn't do that, and so they preserve, one, this very dark color, and two, a fair amount of water. So
じゃあ、
some of these objects are a few percent covered by mass, and
Yeah.
there's arguments actually as to exactly where the Earth's water came from. A lot of it may have been boiled off when the Earth formed and then delivered later by objects from the outer solar system, where there are more of these carbonaceous ones getting thrown in and then hitting the Earth. All right. So most of these objects are in the main asteroid belt. Spacecraft flying through the asteroid belt on their way to somewhere else, you can arrange to fly by an asteroid if you want to. You don't have to do that. You actually deliberately steer yourself to pass nearby. But we have also visited a few near-Earth asteroids with spacecraft. And those are the highlighted ones there. Now there's widely varying size here. I mentioned Lutetia is 132 kilometers wide. There's lots of main-belt asteroids that big. No near-Earth asteroid is that large. Eros, which you see down here, is the second largest one. It's a bit over 30 kilometers from end to end. Ganymede is just a little bit bigger than that. But we have this whole distribution of sizes, and there are more small ones than large ones. So I'm going to zoom in now on that dot, which is the near-Earth asteroid Itokawa, because it's typical for a lot of the other objects that I'll be talking about. It's only a few hundred meters across. There's about 1,000 near-Earth asteroids larger than 1 kilometer wide,
エネルギ
and there's many more of these smaller things. This is what a rubble pile looks like when you zoom way in on it. As advertised, it's a pile of rocks. But it's a very interesting pile of rocks because of the environment we're in here. So, Itokawa is 540 meters. Call it a third of a mile from one end to the other. For comparison, the International Space Station is 100 meters wide. That's the scale we're talking about. That's how small this thing is. Although it's still fairly big
Yeah.
compared to, say, the International
Yeah.
Space Station. It's just very small compared to planets. It's 100 meters across that single largest block that we see on Itokawa. And then there's a whole distribution of particles down to very, very fine grain dust. This is what happens when you have repeated collisions. You just fracture the entire body and repeatedly break it apart and pieces reaccumulate. Because the gravity on something 500 meters across is so low, physics gets very weird. You could not stand on Itokawa if you were to go to Itokawa. Any slight twitch of your muscles, you would fling yourself in your spacesuit off the asteroid and out into space. And you might not come back down again, because that's how low the escape velocity is. And it's like all the other asteroids I've shown you, and all but the couple largest ones, it's very obviously not round. So we've got what look like roughly two ellipsoidal pieces sitting on each other, but they don't slump down, even though they are unconsolidated gravel and other sizes of rubble, because there is less pressure in the middle there than there is if you stick your hand and put it on the table underneath your hand. That is how little pressure is on the inside of these objects. So it doesn't take much strength for them to hold themselves in quite Council at the University of Maryland, many others have worked on this. The gravity here is so low, you have solar wind coming in, depositing protons and electrons. You can charge up actually fairly sizable grains of material and levitate them. And they can migrate around the surface and resettle elsewhere. We also, particularly importantly for the near-Earth objects,
トレイルランナーよく
have to
走
worry
る
about
な。
effects of radiation pressure. So, sunlight has energy and momentum. It doesn't have any mass, but it has energy and momentum. So if you shine sunlight on the surface, there's a very weak pressure being exerted. Again, not something we normally worry about for geology, but when the gravity is tens of thousands of times less than we have on Earth, it becomes significant. This has been studied by astronomers actually for quite a long while now. About a century ago, Ivan Ostrovich Yarkovsky first figured this out on a theoretical basis. It wasn't observed actually happen for decades afterwards. But it's called the Yarkovsky effect. So you have an asteroid out in space, we have the sun, it's spinning. Everything is spinning to some degree. Some asteroids spin more than others. You have the afternoon side of the asteroid. That is the spot where it's the hottest. So there's the most infrared light coming off the asteroid, that part. On the night side over here, it's relatively cold. Less infrared coming off the surface. Infrared heat is also, photons are also light. They carry momentum. It's not balanced. So there's more pressure being exerted this way due to there being more photons going off in the opposite direction. Newton's third law. There's an equal and opposite reaction. When photons go out, the asteroid gets pushed the other way. The key point about the Yarkovsky effect